Okay, so let's start again. So criteria of stability, it shows that in this region of composition, if you mix two liquids, they'll be unstable and they will split into two liquids of composition M and N in different proportions depending on the composition, depending on where this actual mixing composition is, right? And we have seen how to is the ratio of these two liquids by Lever-Arm principle. So when you mix two components, and if they do not satisfy the stability criteria, they are split into two phases. And if these phases are at thermodynamic equilibrium, the phenomenon is an example of LLE or liquid liquid extraction, which is used for solvent extraction. And there is a very important mass transfer operation, which I think is studied in second semester. Okay, so equilibrium criteria for liquid liquid equilibrium are the same as for VLE, because we have not said that at that time it is VLE or LLE, just equilibrium. So what we derived for equilibrium was for all equilibria, VLE, LLE and SLE. We'll see SLE after this. That is solid liquid equilibrium. So we had said that temperature has to be same in both the phases, right? For vapor phase and liquid phase, pressure has to be same for both the phases, right? Where alpha and beta are the phases, and viscosity of component I in the solution has to be same in both the phases, right? किसी को ये equilibrium criteria. So with activity coefficient, this becomes xi for alpha phase into gamma I for alpha phase into pure component viscosity for alpha phase or I component is equal to xi for beta phase, gamma I for beta phase, and viscosity for pure component I in beta phase. If each of these species exists as liquid at system temperature T, right, pure components, then Fi alpha equal to Fi beta equal to pure component viscosity, right? That's what it is. And therefore this equation, this will reduce to this equation 1. Fi will cancel out, and what we'll get is xi for alpha phase into gamma I for alpha phase equal to xi for beta phase into gamma I for beta phase, where this gamma is function of composition and temperature. So if you write for a binary system, you'll get x1 for component 1 in alpha phase, gamma 1 for component 1 in alpha phase equal to x1 for component 1 in beta phase into gamma 1 for component 1 in beta phase. Similarly for component 2, and we can write component 2 is, instead of x2 we can write 1 minus x1, and we'll get equation 4. So any questions on equation 2 and 4? Okay, so we can apply equation 2 and 4 for liquid liquid equilibrium. So we have two equations and three variables. Variables are x1 in alpha phase, x1 in beta phase, and temperature, right? So if you fix one variable, that means if you fix the temperature, then we can solve equations 2 and 4 to get the values of x1 for alpha phase and x1 for beta phase. If you take equation 2, it gives gamma 1 for alpha phase divided by gamma 1 for beta phase is equal to x1 for beta phase upon x1 for alpha phase. Or you can take ln of both the sides and we get equation 5. Okay. Similarly, equation 4 will give this equation 6, similar to how we derived equation 5. Any questions on equation 5 and 6? Okay. So now let's look at phase rule. Phase rule is 2 plus C minus P. And if you look at LLE, we have two phases. So if you put this, you get F is equal to C. And if you consider two components, binary system, then F is equal to 2, right? And so we need to specify at least two intensive properties, and we already specified temperature and pressure, so the system is well defined. Any questions, doubts on what we have done so far? Basically, we started with equilibrium criteria and derived it for LLE. Okay. So now let's look at what are the phase diagrams for liquid equilibrium. And this is, we are looking at first binary LLE, that means only two components. Okay. So we get three kinds of graphs. If you plot temperature versus composition on the x-axis, you get these three graphs, this or this or this. You'll see all these three. Okay. And this curve, which is like an X-shaped curve in A, is called binodal curve. There are two nodes at the top and bottom. And essentially, it's an island in this TX diagram. Okay. So it shows two coexisting phases. In this case, UAL, if you look at UAL, that is left hand side, right? So if you're plotting alpha, this is x1 alpha, this is x1 beta, right? So UAL on the left hand side curve, this side, is for alpha rich phase. So alpha phase rich in species 2. So when you talk about you're plotting x1, x1 is 0 to 1, that means x2, for x2 it is 0 here, 1 here. Right? On the x-axis it is x1, 0 to 1. So for x2 it is going to be 1 to 0. So that means on this side x2 is more, x1 is less, that is rich in species 2. And UBL, that is this side, is beta phase, which is rich in species 1. Is this understood? Okay. Okay, so equilibrium composition x1 alpha and x1 beta defined by intersection of horizontal tie line with binodal curve. So if you look at tie line, is essentially this line which is connecting A and B. And that wherever it intersects, so if I take this one, suppose I take another tie line here. So then this is alpha, x1 alpha, and this is x1 beta. So depending on where I am taking it, it will be different. And TL, the lower point, this temperature, is the lower consolid temperature or lower critical solution temperature. See, in this phase, in this region there are two phases. Here it is one phase. Here also it is one phase. So here it is homogeneous. Outside this island, it is all homogeneous. So at this temperature, that is TL, Below this temperature, it is homogeneous phase, one phase. That means both the liquids components mixed together. They are soluble in each other. And about TU, that is upper critical solution temperature, also it is single phase, and we have homogeneous liquid. Only in this region we have two phases. So this TL is called lower critical solution temperature, and TU is called upper critical solution temperature. So that is the maximum temperature at which the two liquid phase will exist, TU, and TL is the minimum temperature at which the two liquid phases exist. Below TL it is one single phase, above TU it is one single phase. Okay. Any questions on LCST, lower critical solution temperature, and UCST, upper critical solution temperature? So at the temperature between
सर
TU and
मतलब लोअर क्रिटिकल सॉल्यूशन पे वो सॉलिड होगा क्या मिक्सचर या सिर्फ लिक्विड लिक्विड ही रहेगा?
liquid ही है पूरा. Only in that island, in that anda, it is two liquid phases. Above that, it is one single liquid phase. Below that, it is one single liquid phase. There is no solid. It is liquid.
मतलब वहाँ पे फ्रीज नहीं होगा ना, ऐसा कुछ नहीं है?
Freeze नहीं हो रहा है. We are not talking about freezing here. We are talking about liquid equilibrium. It's not freezing और नीचे जाएगा, बहुत नीचे जाएगा. We are not looking at freezing point here. We are looking at तो liquid रहा तो equilibrium क्या होता है. Freezing अभी देखेंगे when you look at solid liquid. Okay. ठीक है. So between TU and TL, it is LLE, that means two liquid phases, and at temperatures less than TL and greater than TU, it is single phase. Okay. So considered times temp points or LCST and UCST are limiting states of two-phase equilibrium, for which all properties of two equilibrium phases are same. Okay. So these are two limiting phases points for equilibrium. Okay. Any questions on A part, A diagram, before we proceed to B? Okay. So behavior of figure A is very rare. एक आध केस होगा जो ज़्यादा होगा. But when, जैसा तुम पूछा, freezing curve, right? When LL intersects freezing curve, only UCST exists. जैसे यहाँ पर देखा हमने, right? So LLE जो है, ये जो लिखा है LLE, if it intersects a freezing curve, only this will exist, UCST. And when it intersects a bubble point curve, only LCST exists. जैसे ये है. So इसके ऊपर वेपर है. There is vapor here, and there is a solid here. Okay. So any on A, B, and C, on all these three diagrams, as we see in this, M will separate into two phases. जैसे ये M लिया तो यहाँ पर दो फेज हो जाएगा. ये M लिया तो यहाँ पर ये दो फेज हो जाएगा. यहाँ पर ये M लिया तो ये दो फेज हो जाएगा. So any point in this region of two phases will separate into two immiscible liquids, and compositions are given by this and this, or this and this. And the relative amounts of two phases are given by inverse lever arm principle. Amount of phase A divided by amount of phase B is equal to line MB upon line AM. पहले भी देखा था हमने, right? BLE में. the amount of A and B will be ulta. If you're talking about this is A phase, alpha phase and beta phase, so ये जो है MB upon AM. So if I take A phase, this is A phase, so amount will be this thing. If I talk about B phase, amount will be this thing. Similarly, यहाँ भी अगर लिया हमने, amount will be this for A phase, this is A phase, और B phase के लिए amount will be this one. Similarly for this one also same thing. A phase के लिए amount will be this one, and for B phase amount will be this one. ठीक है? Any questions on these three diagrams? Generally यहाँ पर LLE पे सिर्फ एक short note ही आता है, and you have to write all these things. ये diagram at least draw करना चाहिए because diagrams and explanations. और ये स्मिथ में से लिया है, आपने इसमें नहीं दिया है नारायण में. Okay. And sometimes they ask you the three types of solubility diagram.
सर
Yeah.
सर वो लिक्विड लिक्विड में दो फेजेस मतलब
So if I take say benzene and water, right, they'll not mix together, right? Maybe some liquids which are miscible in some region mix हो जाता है, in some region they are not mixing, तो separate हो जाता है, दो फेज separate हो जाता है. जैसे एक एग्जांपल है ऑयल एंड वाटर, वो किसी भी कंपोजिशन में मिक्स नहीं होता है, राइट? इफ यू टेक सम ऑयल एंड वाटर सेपरेट हो जाएगा, बट देयर आर कंपाउंड्स व्हिच विल मिक्स इन सर्टेन रीजन. या
सर फेज तो एक ही होता है ना लिक्विड.
नहीं, टू सेपरेट इनसॉल्युबल फेजेस. अभी आप देखोगे, अगर आप घर पे जाके देखो, वो पानी और ऑयल मिक्स करो, राइट, एनी ऑयल, जितना भी घुमाओ उसको, बाद में यू कैन सेपरेट, ले ऑयल ऊपर आ जाएगा, पानी नीचे हो जाएगा, राइट? There are
हाँ सर.
two liquid phases, which are insoluble in each other. That's what we talk about when we say LLE. That means, जैसे हमने experiment बताया था last time. I can show that again. If you take, say, let me show that so that you can recall. Okay, let me do that. Can you see this? दिख रहा है ये?
Yes, sir.
Yes, sir.
The technique of liquid-liquid extraction is a form
Can you hear also?
Yes, sir.
Yes.
Yes, sir.
of solvent extraction, which is often referred to simply as a separation. And we do this using the technique of liquid-liquid extraction is a form of solvent extraction, which is often referred to simply as a separation. And we do this using a separating funnel as shown on the screen. The technique can be used in a range of contexts, and it's important that you understand why you're carrying out a separation in the experiment that you're doing. In this demonstration, we have a solution of a product of a reaction in an organic solvent, which in this case is diethyl ether. We are going to wash the solution with water to remove impurities which are water soluble. The first step is to remove the magnetic stirring flea from the reaction flask, and we need to wash this with ether to ensure that we don't lose any of our product. We now need to pour the solution of our product into the separating funnel, taking care to avoid any spillages. So it's wise to use a small glass funnel as we pour. Then we can rinse our reaction flask with more ether to ensure that no product is lost. Now we add the water which we're using to wash our reaction mixture with. It's important that you pay attention to your script, which may specify a different solvent and a particular volume that you need to work with. Next, you need to place a stopper in the neck of the separating funnel, and you must ensure that you don't allow this to fall out at any point while you're handling the apparatus. Secure the stopper with one hand and carefully invert the separating funnel. Now you can gently shake the funnel while periodically opening the tap to release pressure. Normally you carry out these steps several times to ensure thorough mixing of the two layers. And then with the tap closed, you can carefully replace the funnel in the ring on the clamp stand. Here you can clearly see the two separate layers in the funnel. In this case, the denser aqueous layer is at the bottom and the ether layer is on top. However, you should never make assumptions about which layer is which, and you may be given instructions that tell you how to test which layer is organic and which is aqueous. Before running any solvent out of the funnel, you must first remove the stopper. Not doing so is a common error which will prevent the solvent from running freely. Now you should place an appropriately sized conical flask under the separating funnel before carefully opening the tap to allow the lower layer to run out. You should watch patiently as the interface between the two layers moves towards the tap so you are able to stop the flow once all of the lower layer has been removed. Remember that in this case, the lower layer was the aqueous layer. Now you can remove this flask and place a second clean conical flask under the separating funnel to collect the upper layer. As always, you should check your script to see what you've got to do next. You may be expected to return one of the layers to the separating funnel to carry out further extraction steps. In this case, however, we are simply going to dry the organic layer using magnesium sulfate. Other drying agents that may be used could include calcium chloride and sodium sulfate, so make sure you read the script before proceeding. If the drying agent forms clumps as shown here, that's a sign that the solution is still wet and that more drying agent is required. When you can see a snowstorm effect like this, you know that the solution is dry and that no more drying agent is needed. You can now remove the drying agent by gravity filtration before consulting the script once again to identify your next step.
Okay. समझ में आया लोगों को?
सर मतलब वो इमिसिबल मिसिबल वो दो फेजेस लेके किया है क्या, मतलब अगर वो इमिसिबल
Generally what happens, when you do a reaction, either it will be an organic phase or an aqueous phase, right? अगर यहाँ पर organic phase दिखाया ether में है, right? Some reaction has taken place. I want to extract the valuable compound from our ether or separate. तो उसमें क्या किया, जो valuable compound है, नाम नहीं दिया है यहाँ पर, doesn't matter. So you mix with water because it is more soluble in water देन इन ईथर। सॉल्व सॉलिबिलिटी का खेल है एलएलई में, एक्सट्रैक्शन में। सो द वैल्यूएबल कंपाउंड विल डिसॉल्व इन वाटर, इसमें वही हुआ यहाँ पर, व्हेन यू मिक्स इट टुगेदर, जिसमें ज़्यादा सॉलिबिलिटी उधर जाएगा, राइट, तो उधर जाके वो डिसॉल्व हो गया, और ईथर में सॉलिबिलिटी उसका कम रहेगा तो रिलेटिवली कम रहेगा, थोड़ा रहेगा डिपेंडिंग ऑन सॉलिबिलिटी कितना है ईथर में। 100% सेपरेशन मुश्किल होता है अनलेस इट इज कम्प्लीटली इनसॉल्युबल। तो अभी क्या हो गया, वाटर एंड ऑर्गेनिक ईथर आर नॉट मिसेबल। तो उसमें क्या हो गया, दो लेयर बन गया, एक एक्वियस लेयर हो गया जिसमें अभी जो डिजायर्ड प्रोडक्ट है वो डिजॉल्व हो गया, और दूसरा ईथर लेयर हो गया। समझा क्या?
हाँ सर, समझा।
तो अल्टीमेटली यही होता है कि जब जब हम रिएक्शन करते हैं, एनी केमिकल रिएक्शन, वी वांट टू, देयर आर मेनी, actually जब when you do any reaction, you always do reaction in some solvent. Generally some solvent is there in which reaction happens, and there are many ways of finding or getting the pure product. One of them is distillation. अगर boiling point difference रहेगा solvent and valuable product का, तो then you can do distillation. अगर boiling point difference नहीं रहेगा or if they are very close to each other, then you go for solvent extraction. Then you find a solvent which is able to dissolve the valuable compound, and then you mix it with that reaction mixture. यहाँ पर हमने simple lab experiment बताया, but there are extraction columns in which you can have what you call light organic layer coming from the top, uh, and aqueous layer coming from the top, and organic layer coming from the bottom, and they will mix with each other. There will be mass transfer. सो ऑर्गेनिक लेयर से एक्सट्रैक्ट हो जाएगा एक्वियस लेयर में, या एक्वियस लेयर रहेगा तो एक्वियस से ऑर्गेनिक में एक्सट्रैक्ट हो जाएगा, डिपेंडिंग ऑन व्हाट इज द सिस्टम। एंड देन व्हाट यू कैन डू इज यू कैन सेपरेट इट आउट बाय डिस्टिलेशन। अगेन डिस्टिलेशन तो आएगा ही, बिकॉज सॉल्वेंट रिकवर करना है हमारे को, बिकॉज जो वैल्यूएबल प्रोडक्ट सॉल्वेंट में आया तो अगेन सॉल्वेंट ऐसा सिलेक्ट किया जाता है कि वी शुड बी एबल टू सेपरेट सॉल्वेंट बाय डिस्टिलेशन एंड गेट द वैल्यूएबल प्रोडक्ट।
यस सर।
ओके, so let us continue from there. Okay, so this is what binary system, but generally there are three components, right? दो में दो का सिस्टम बहुत कम रहता है। जनरली इन केमिकल इंजीनियरिंग वी हैव थ्री कंपोनेंट सिस्टम, बिकॉज यू हैव, जैसे हमने देखा, राइट, एक ऑर्गेनिक लेयर था जिसमें वैल्यूएबल प्रोडक्ट था, और हमने वाटर ऐड किया, थर्ड कंपोनेंट। तो देयर बी नॉर्मली थ्री कंपोनेंट्स, राइट। तो उसके लिए ये बाइनरी सिस्टम यू कैन प्लॉट ऑन एक्स वाई डायग्राम, बट टर्नरी सिस्टम रहेगा तो देन वी हैव अ टर्नरी एलएलई, दैट वाज बाइनरी व्हाट वी सॉ सो फार, but then we generally have three components. So that is called ternary LLE, and we use a equilateral triangle diagram to draw these things. So generally what happens, equilateral triangle रहता है ऐसा, डायग्राम आता है ग्राफ पेपर के समान आता है, जस्ट लाइक यू हैव अ नॉर्मल rectangular graph paper, you have a ternary or equilateral triangle also in graph paper. And then what we do is, it say there are three corners of this triangle are three components. So we can say this is, say, A component, this is B component, and this is C component, right? तो यहाँ बताया, and जो perpendicular रहता है, if we say take the perpendicular from here to here, गलत आ गया ये, so take perpendicular from apex, So if I draw the perpendicular from apex, that represents 100% of component C. Similarly, यहाँ का perpendicular जो रहेगा, it will be 100% of component A. And यहाँ से जो रहेगा, that is 100% of component B. That's what I've shown here, right? And on the x-axis, you can draw, जैसे ये लिया मैंने, point A लिया, component A, component B, right? So it is 0 to 100%, that is 100% B है ये, और ये 100% A है. So on this side it is 0 to 100 B and this is 0 to 100 A. Similarly, B यहाँ पर रहेगा और C यहाँ रहेगा, तो you can have different compositions here. 100% C is this, 100% B is this, and similarly यहाँ पर 100% C is this and 100% A is this. So these three sides of the equilateral triangle represent the compositions of three phases. And if you have any point, if you get any point on this equilateral triangle, suppose I get a composition like this, right? I want to find the composition of this point. So what I do is I draw a perpendicular from this point to each of these sides. ये तीन perpendicular draw करने का, and this will give us the composition of each side. So this is percentage C, this y perpendicular, this is percentage B, percentage sorry opposite वाला, ये opposite वाला रहेगा, ये opposite वाला, this is percentage A and this is percentage B. That's what I've shown here, right? Percentage B opposite apex का रहेगा, percentage A opposite A का रहेगा, और percentage C opposite C का रहेगा. So that's how we find the composition of any point on an equilateral diagram. Okay. So sum of perpendicular distance from any point in a triangle to the sides is altitude of triangles. ये हमने ऐड किया, suppose I add this plus this plus this. This will be equal to this height, which is representing 100%. Altitude represents 100% composition, and distance to the three sides represent percentage or fractions of the three components. समझ में आए? Okay, so if I take any point D, suppose I take this point D, this is say 0.2 है, so that means it is 0.2 or 20% B and 80% A. And all points on DC, ये जो vertical line draw किया, represent mixture containing 80% A and 20% B. So if I take anything here, it is 20% B and 80% A. So that is how equilateral triangle is used for representing the ternary LLE. ठीक है? हाँ, एक्चुअल डायग्राम जो रहेगा, जो हमने देखा था, राइट, वी हैव सीन दिस फॉर two components, it was like this. So three components, it will be something similar, but it will be on ternary diagram. See this, ऐसे डोम शेप्ड आएगा यहाँ पर भी डोम आया था बीच में, we had a dome here, right, in the center. It was a dome. Similarly, we get dome here also on triangle equilateral triangle diagram because it's a 3-component system. और इसमें भी जैसे ये if I look at this one, this is A rich because this is 100% A and this is B rich. कोई point लिया यहाँ पर. This is A rich point and this is B rich point. That means more of B here and more of A here. And you have जैसे if you look at A and C are completely miscible. Okay, C dissolves completely A and B. So A and C ये जो है completely miscible है. B and C completely miscible. It's only A and B which is immiscible. 3 component में से. A and B do not mix together. A and C mix together completely. B and C mix together completely. Right? A and B dissolve to a limited extent in each other and give. That's why we get 2 phases. Solubility बहुत कम है एक दूसरे में. That's why we get 2 phases of. One is A rich and one is B rich. 2 phase मिलेगा. And this curve is a binodal solubility curve. Outside this region, it is homogeneous phase. ये सब ये homogeneous है, one liquid phase है. But inside this, we'll get 2 liquid phases. जैसे वहाँ देखा था ऊपर में, right? We have seen that before also. Outside this is single phase, inside this is 2 liquid phases. So यहाँ पर भी for a ternary diagram. Outside this, it is 1 phase. Here it is 2 phases. Okay. So any ternary mixture, suppose you take a point M here, it will form 2 insoluble saturated liquid phases. One will be A rich and one will be B rich. One is called raffinate phase, R is affinate and E is extract. Extract is actually जहाँ हमारे को desired product चाहिए. Raffinate is which is not desired. So you'll get some point, एक point लिया हमने, so it will be separating into 2 phases, which will be this. R and E, and this is called tie line. जो connect करता है R और E को is called a tie line. Okay. And the what you call and the react mole what you call weight fraction of component raffinate and extract is given by this thing, this perpendicular from this point. Suppose this is R and E. Right, ये tie line के लिए तो ये perpendicular draw किया हमने तो this is extract का कितना percentage है ये raffinate का कितना weight percent है. It gives the ratio of these two. Weight fraction of C in raffinate, weight fraction of C in extract. Okay, any questions on ternary LLE? You'll be actually doing problems in LLE when you do mass transfer. यहाँ पर just introduction ही है, just to understand how the phase diagrams are understood. Understanding phase diagrams for binary and ternary systems. ठीक है, any questions on LLE? इतना ही है, ज़्यादा नहीं है, ज़्यादा हम करेंगे भी नहीं, because this is essentially to explain what happens in LLE liquid-liquid equilibrium. समझ में आया क्या? थोड़ा डिफिकल्ट है because they have not seen any ternary or equilateral triangle diagram. कोई देखा है क्या? Have you ever seen a equilateral triangle diagram?
No,
No, sir. So जाके Google में search करो, you'll definitely find it. That's why just an introduction की ternary diagram क्या होता है, उसमें composition कैसे represent करते हैं, और how do you find, if you take any point, how do you find the composition of that point? So percentage A कितना है, B कितना है और C कितना है, and what is the LLE और dome for LLE ternary diagram. जैसे dome रहता है, जैसे binary के लिए वैसे ternary के लिए. ठीक है. This you can find in Narayanan, but ternary का इसमें नारायण में दिया है, but binary का ये सब जो डायग्राम है, ये स्पेस से लेना पड़ेगा आपको. ठीक है. Any questions on liquid equilibrium? शांति है एकदम. कितने लोग को नहीं समझ में आया? सबको समझ में आया लगता है. Nobody is raising hands. दीक्षिता समझ में आया क्या? देवेंद्र?
सर थोड़ा थोड़ा.
थोड़ा डिफिकल्ट कॉन्सेप्ट है. It's a little difficult, but you need to actually go back and read it. इसमें ज़्यादा कुछ नहीं है, सिर्फ डायग्राम अंडरस्टैंड करने का है, और वो डेरिवेशन है. डेरिवेशन तो कुछ नहीं है, डेरिवेशन वाज सिंपल फ्रॉम इक्विलिब्रियम.
सर सिंगल फेज इन द टू
डेरिवेशन
फेज
सिंपल, ज़्यादा कुछ नहीं, बट अंडरस्टैंडिंग दिस डायग्राम्स टेक्स अ लिटिल टाइम. क्या बोल रहे हैं?
टू फेज डायग्राम में जो सिंगल फेज है ना,
Hello. Hello, can you hear me? हेलो.
यस सर.
क्या क्वेश्चन था आपका?
Sir, single phase, does it mean that the two components are mixed in that phase?
Yes. When you talk about a single homogeneous phase, that means they are soluble in each other. That means एक single phase, जैसे हम if we take say ethanol and water, right, they will be miscible. Mix हो जाता है, एक single phase बन जाता है homogeneous. But if I take toluene and water, they will not mix. दो separate phase बन जाता है. तो ये जो diagram बता रहे हैं हम, we are talking about a region in which there are two separate liquid phases. That's why it is liquid equilibrium. जैसे वेपर लिक्विड इक्विलिब्रियम था ना, वी आर टॉकिंग अबाउट टू फेजेस, दैट मींस वेपर एंड लिक्विड एंड इक्विलिब्रियम बिटवीन वेपर एंड लिक्विड. इन दिस केस वी हैव टू लिक्विड्स एंड दैट्स इक्विलिब्रियम. दैट मींस जैसे हम वेपर में देख रहे थे, राइट, वीएलई में कंपोनेंट गोज फ्रॉम लिक्विड टू वेपर, राइट. देयर इज अ कंपोजिशन yi of component I in the vapor phase and xi of component I in the liquid phase, right. That is the equilibrium composition. Similarly यहाँ पर अगर लिक्विड लिया हमने, जैसे दो फेज लिया अल्फा एंड बीटा, ए एंड बी, सपोज दो लिक्विड फेज है, तो उसमें क्या रहेगा, वील सी दैट कंपोजिशन ऑफ कंपोनेंट आई इज से xi in alpha phase, composition of component I in beta phase is xi or beta phase, right, जो मैंने दिखाया था पहले. If you remember the derivation which I did, right, यहाँ पर जो डेरिवेशन किया था, it was actually showing कि ये जो कंपोजिशन है, कंपोजिशन that means more fraction of component 1 in beta phase and more fraction of component 1 in alpha phase. That is showing instead of y and x, it is x1 in alpha phase and x1 in beta phase. Just think about VLE. Instead of VLE, just replace V with L and you get liquid equilibrium. So there will be distribution of each component between the two phases, alpha phase and beta phase. Alpha phase में component 1 रहेगा, component 2 रहेगा, component 3 रहेगा. Similarly, beta phase में component 1 रहेगा, component 2 रहेगा, component 3 रहेगा. But the concentration will be different in alpha phase and in beta phase. ये हमने किया था बाइनरी सिस्टम के लिए. सिमिलरली देयर विल बी टर्नरी सिस्टम का अलग इक्वेशन आएगा. समझ में आया दीक्षिता?
Yes, sir. But phase rule में phase should be equal to 1.
No. Phase is not one. When you say two liquid phases, that is two phases. There can be two liquid phases, there can be two solid phases also. We'll see examples in the next unit. You will see two solid phases because they are not mixing with each other. Miscible है तो one phase है. If two liquids dissolve in each other, say ethanol water, so then it is one phase. But if I take toluene and water, there is two phases, two liquid phases. Separate हो जा रहा है वो. I can identify two separate liquid phases. अलग अलग दिखता ही है हमारे को, जैसे अभी दिखाया हमने वीडियो में दिखाया, राइट. देयर वर टू लिक्विड फेजेस. इट इज नॉट सिंगल वन फेज. फेज डजंट मीन जस्ट लिक्विड है कि वेपर है. इट इज सेपरेटली कितना दिखता है मेरे को. वेपर में जनरली एक ही दिखता है. यू डोंट सी टू सेपरेट वेपर फेजेस, बट लिक्विड में दो हो सकता है, सॉलिड में दो हो सकता है. एंड वील सी एग्जांपल्स ऑफ दैट इन नेक्स्ट यूनिट. सॉलिड में दो फेज हो सकता है बिकॉज व्हेन यू टेक सॉलिड, सपोज आई टेक कैल्शियम कार्बोनेट एंड आई कैल्साइन इट. कैल्सिनेशन ऑफ कैल्शियम कार्बोनेट में क्या होता है कि CO2 is released and what you get is CaCO3 will become CaO plus CO2, right. So if I consider phase rule for that system, we'll see that example. Then it is two solid phases. One is calcium carbonate, one is calcium oxide. They don't mix in each other. You can definitely see separately calcium carbonate and calcium oxide. ठीक है. Is that
Yes,
clear?
sir. Yes, sir.
So tomorrow we'll see solid liquid equilibrium. इसमें ज़्यादा कुछ नहीं है, डेरिवेशन इज वेरी सिंपल, बट अंडरस्टैंडिंग और स्पेंड लिटिल टाइम एक्चुअली थिंक अबाउट इट एंड रीड अबाउट इट। ठीक है, तो स्मिथ का बुक है आप लोगों के पास? है क्या स्मिथ का बुक?
हाँ
यस, नो, डोंट नो,
यस
कुछ तो आंसर होना चाहिए।
है सर, है।
रिप्लाई, ओके, ठीक है। तो चलो स्मिथ का बुक पढ़ो, है ना? तो स्मिथ के बुक में पढ़ो, उसमें लिक्विड इक्विलिब्रियम का ये 3 डायग्राम दिया है।